let's jump right in. This is a technical briefing on one of the toughest challenges in modern civil engineering: how we build massive structures in these impossibly tight urban spots. We're going to skip the glossy architectural renders and get into the raw engineering, the stuff that actually makes these projects possible. So the whole problem starts with a very simple fact. Our cities are packed, and they're only getting denser. The days of just sprawling outwards are pretty much over. If we want to grow, we've got to build inward and upward, usually on sites that at first glance look totally unbuildable. And that brings us to our core concept for today: tight site construction. What we're really talking about is building in the gaps on these tiny postage stamp-sized lots, squeezed right next to active roads and existing buildings. You know, this isn't just regular construction with a bit less elbow room. It's a completely different game where logistics, precision, and absolute control are everything. Okay, so for our first case study, we're going to Dubai, to the One Za'abil project. The star of the show here is the Link. It's this 226-meter-long horizontal bridge, basically, that connects two towers 100 meters up in the air, right over a busy highway. This thing is an absolute masterclass in precision. So that brings us to the core engineering problem. How do you do that? Tall towers are not static objects, right? They sway in the wind, they settle over time. So how in the world do you surgically implant a 9,500-ton steel structure between two moving targets and make sure it fits perfectly without putting catastrophic stress on everything? And when you look at the challenges, they are just stacked. You've got to account for the fact that these towers are moving independently. You're building one of the world's longest cantilevers over live traffic. Any single one of these would be a huge deal on its own. Here, they were all happening at the same time. The solution was all in this sequence. It had to be meticulous. First, they built the towers up. While that was happening, the Link was actually assembled down on the ground, where they could control the quality and alignment perfectly. Then came the main event, lifting it into place. They used something called strand jacks. Think of them as a whole system of powerful hydraulic jacks that slowly pull on steel cables. The lift took days and required constant real-time monitoring and these tiny micro-adjustments to get it to line up with the connection points. And that's the big takeaway from Dubai. The temporary stuff, the structures that help you build, the step-by-step process, the how, is just as critical to the engineering success as the final building you see today. That incredible lift was temporary work, but it was arguably the single most important piece of the whole project. All right, next up, let's jump over to Mumbai. We're talking about one of the most densely populated places on Earth. For the Sky Towers project, the puzzle wasn't connecting things up in the air, it was how to build from the ground up when you have absolutely no ground to work with. I mean, think about that for a second. That question completely changes how you approach construction. When you have no laydown area, no space to store steel, rebar, anything, the whole traditional model just goes out the window. You can't bring materials to the site to wait. You have to bring them directly to their final spot in the building, the moment you need them. So the constraints here were all about logistics and the environment. Besides having literally nowhere to put anything, the site was wedged between residential buildings. That meant noise and disruption had to be kept to an absolute minimum. And to top it all off, you have to manage all this during Mumbai's heavy monsoon season, which just adds another layer of chaos to a job that's already on a narrow, vertical footprint. The solution here was brilliant. You make the building its own factory and its own storage yard. They used self-climbing formwork systems. These are the molds for the concrete walls that literally inch their way up the structure as it gets taller. Concrete gets pumped hundreds of meters straight to where it's needed, and every single delivery of steel or glass is scheduled just in time, arriving on a truck to be immediately picked up by the crane and installed. So the key lesson from Mumbai is pretty clear. In these super dense cities, you have to master vertical logistics. It's not optional. The efficiency of your cranes, the timing of your deliveries, that becomes the lifeblood of the entire project. Okay, for our final case study, let's head to Singapore. This is a city that has one of the most complex, most heavily regulated construction environments anywhere. Here, the biggest worry isn't just the building itself, but what building it does to the city's massive network of underground infrastructure. Now, this is a question of control. When you're digging a massive hole just a few meters away from active subway lines, tunnels, and utilities, your margin for error is zero, absolutely zero. Any ground movement, even a few millimeters, could have consequences that ripple across the entire city. The constraints are just severe. You've got strict government rules on how much the ground is allowed to move. You're working on sites that can be as narrow as a single lane of traffic. And through it all, the city's public transport has to keep running perfectly, just feet away from your work. So the technique here is all about proactive control. Often, they use what's called a top-down method. It's kind of counterintuitive. First, you build these deep, super rigid walls into the ground. This basically creates the box for your basement before you've even dug the hole. Then you start digging down, but as you go, you build the basement floors from the top down. Each floor slab you pour acts like a massive internal brace, holding the walls in place and stopping them from moving. And the entire time, thousands of sensors are monitoring every tiny movement in the ground in real time. And that's the crucial point from Singapore. The data is a construction material. That network of sensors and the real-time monitoring system, they are just as fundamental to the safety and the integrity of that project as the actual concrete and steel. Okay, so let's pull all these lessons together. Each city we looked at had a unique main problem, which in turn forced a specialized engineering solution. And when you put them all together, they start to form a kind of playbook for how to do this kind of work. This table really lays it out. In Dubai, the constraint was connection, and the solution was all about precision lifting and sequencing. In Mumbai, the constraint was space, and the solution was vertical logistics. And in Singapore, the constraint was safety and vibration, which was solved with top-down methods and constant monitoring. You can see how each solution is a direct answer to the site's biggest problem. And this really defines the job for any engineer on one of these projects. Success is not just about the final design. It demands incredible precision in your planning, designing temporary works with the same care as the permanent building, using real-time data to guide every move, and then, of course, flawless execution. Ultimately, this is the new reality of how our cities develop. All the easy sites are gone. The future isn't about growing out into empty fields. It's about skillfully, intelligently, and safely growing upward and inward, filling the gaps with some truly brilliant engineering. This isn't science fiction. This engineering is happening right now. It really just leaves you with one final question. Now that we've conquered these impossibly tight spaces between our buildings, what is the next impossible frontier that we're going to learn how to build in?
If you're ready to level up, like and share this video. Subscribe and hit the bell to join the future of efficiency. Aira, your life optimized.